Discrete mathematics is a very important branch of mathematics. Now we start with unit number 2 of discrete mathematics, that is lattices and Boolean algebra. Now next is distributive lattice. A lattice L is said to be distributive if the following distributive properties are satisfied for any elements A, B, C in L. First is A meet B join C is equal to A meet B join A meet C, means meet is distributive over join. And second is A join B meet C is equal to A join B meet A join C, means join is distributive over meet. So if both the distributive laws are satisfied for all A, B, C and L, then that lattice is said to be distributive. Now to show that the lattice L is not distributive, it is enough to find one triplet of elements A, B, C and L such that at least one of the distributive properties is not satisfied. But to show it is a distributive lattice, we have to show both the laws for all elements A, B, C in L. Now let X be any non-empty set and Px be the power set of X. Then under set inclusion relation, Px forms a lattice. Since for any ABC belonging to Px, A join B is A union B and A meet B is A intersection B. That is an element of Px again. Now remember, for set inclusion relation, A join B means least upper bound of A and B is their union, and A meet B means greatest lower bound of AB is their intersection. Now for distributive lattice we check both the laws. Now for any ABC belonging to Px, first consider A join B meet C. So at join is union and meet is intersection, it is A union B intersection C. Now as union is distributive over intersection, by set theory this is A union B intersection A union C. But A union B is A join B and A union C is same way A join C. So it is A join B meet A join C, means the second law holds. Now for first law, in the same way, A meet B join C is equal to A intersection B union C. Again by set theory it is A intersection B union A intersection C. But as intersection is meet and union is join, this is A meet B join A meet C, means first law also holds, and hence Px with union intersection is a distributive lattice. Now third is complemented lattice. Now L join meet be a bounded lattice with greatest element 1 and least element 0. A belongs to L. An element B in L is called as complement of A if A join B is 1 and A meet B is equal to 0. It means if there exists some element B in L such that A join B is 1, that is greatest element, and A meet B equal to 0, least element, then B is called as complement of A denoted by A dash or A bar. Now if every element of a bounded lattice has a complement, then the lattice is called as a complemented lattice. Note that complement of 0 is 1 and complement of 1 is 0. It means complement of least element is the greatest element and complement of greatest element is the least element. At the same time, if A is a complement of B, then B is complement of A. Now see illustrative example. Consider the diamond lattice L represented by following Hess diagram. Now here L is a bounded lattice as D is the least element and C is the greatest element. Now we find complement of each. Now as B and C are least and greatest elements, obviously D complement is C and C complement is D. Now what is A join B? Now A join B is least upper bound of A and B, that is C, and A meet B is D. So what is complement of A? It is equal to B. Now if A complement is B, then obviously B complement is equal to A. And as C and D are greatest and least elements, directly also we can say that C complement is D and D complement is C. So in this way, every element in that diamond lattice has a complement, and so it is a complemented lattice. Now by definition, complement of A is an element B such that A join B is the greatest element and A meet B is the least element. Now, as 1 is the least element and 20 is the greatest element, obviously complement of 1 is 20 and complement of 20 is 1. Now, to find the complement of 2, we need to find an element A from D20 such that 2 join A is the greatest element 20 and 2 meet A is the least element 1. So, in the table of join in the row of 2, observe where we are getting the greatest element 20. So we are getting 20 here, which is in the column of 20. It means 2 join 20 is 20. But for 2 meet 20, we are getting the least element 1. Then we can say that 20 is the complement of 2. For that, observe the table of meet. Now here for 2 meet 20 we are not getting 1, which is least element. So complement of 2 does not exist. Now to find the complement of 4 we need to find A such that 4 join A is the greatest element 20 and 4 meet A is the least element 1. Now observe in the row of 4 in the table of join. We are getting 20 for 5, 10 and 20. Means 4 join 5 is 20, 4 join 10 is 20, 4 join 20 is 20. But for the same element either for 5, 10, 20, if meet is coming 1 then that is the complement. Now observe the table of meet. For 5, 10, 20. 4 meet 5 is 1. So 4 join 5 is 20 and 4 meet 5 is 1. So condition is satisfied. So complement of 4 is 5. Then 4 meet 10 is not 1. 4 meet 10 is not 1. Same way 4 meet 20 is not 1. So complement of 4 is 5. Similarly, we can find complements of 5, 10. So this is the table. Complement of 1 is 20. Complement of 2 does not exist. Complement of 4 is 5. So complement of 5 is 4. Complement of 10 does not exist and complement of 20 is least element 1. But this is not a complemented lattice as complement does not exist for 2 and 10. Now, consider the lattice cell represented by following hash diagram. Find complement of all elements. Again, observing the diagram, 0 is the least element and 1 is the greatest element. So, obviously, complement of 1 is 0 and complement of 0 is 1. Now, for remaining elements A, B, C, we need to find their complements. Now, A join B means least upper bound of A and B is 1. At the same time, A meet B is 0. So, complement of A is B means complement of B is A. Now, consider B join C. So, B join C is equal to 1. And what is B meet C? It is 0. So, complement of B is C and complement of C is B. Thus, every element in L has a complement and hence this is a complemented lattice.